Hi, welcome to the preview chapter um, of Earth Science. And this chapter, we're going to be going over these key points. The first one is to describe the disciplines that are covered in Earth Science. So we're going to talk about what they are and kind of how we can use them. The next thing that we're going to do is be able to evaluate a news story and see how it pertains to Earth Science. There's lots of stuff in the news these days, and we're going to see a lot of it does, in fact, relate to Earth Science. Explain some the key elements of the scientific method, and I'm sure you are familiar with them, but we're going to make sure that everyone is up to speed on the scientific method. We're going to characterize the Earth systems and see its key realms. We're going to state where energy that affects the Earth and other planets comes from. There's different types of energy, and we'll talk about those different energy sources. Then we're going to describe a few key themes that serve the foundations for understanding the Earth and its universe. And then we're going to identify some practical uses that help a background in Earth science can help you understand and address. So this first image is a photograph of Antarctica, and it covers a lot of different aspects of Earth science. We'll talk about some of these different aspects, but it has, I want to point out, it does have a volcano. It has a mountain chain. It's covered in ice, surrounded by water. So lots and lots and lots of Earth science that we're going to be getting into. So when we start talking about Earth science, in the past, there's been a lot of sciences, and we've learned more and more and more, and we've gotten more and more drilled down into different aspects. So when Earth science really began, when we started going into space and seeing how all these interactions between these different fields that we got so specific on, how they all interact. And so we're going to kind of look at four main disciplines that are associated with Earth science. The first one being geology, the study of rocks; oceanography, the study of water; atmospheric sciences, the study of the meteorology and the air and the surrounding us; and then how does the Earth fit into the rest of its solar system and beyond. So as I just got done mentioning, geology is the study of our planet with focus on materials that compose it, the phenomena that change it, and its long-term history. And so we have a geologist doing some field work, and my background is a geologist, and I really liked being a geologist to go out into the field and get dirty, spend a lot of time in nature. And one of the beautiful things about teaching at Mineral Area College is that this area is surrounded by world-class geology. The fact that we're Mineral Area College should give you a clue as how much we value minerals around here in our long mining history. We're about as far away from an ocean as you can get, but we still are going to cover oceanography because it does have a direct impact on us. We will talk about how the oceans interact with the land, and this fall of 2020 we'll talk about hurricanes and hurricane season, and we'll talk about how you can collect data in the ocean, and we can use that data for helping us with modeling ocean currents and also its impact on the atmosphere. Speaking of the atmospheric sciences are usually brought down into two major categories. The first one being meteorology, which is studying of the word meteor means sky. Ology means studied. So these are the phenomena in the sky that affect us, namely weather, which is atmospheric conditions at a given place and a given time. If we kind of zoom out into a longer time period, we'll start looking at something called climate, the region over a longer period of time. And then finally, space science or astronomy. How does the Earth, the study of planets, stars, and other objects as a phenomena in the universe? So as a scientist, the first thing that we want to be doing is making as many observations as we can. And in order to collect data, sometimes we have to go out into the field. And so that was what drew me into geology, was the fact that I got to go out into the field. In fact, when I was a junior at Eastern Illinois, I actually went to this place called Mineral Area, and slept over, went and hung out at Johnson Shut-ins to look at the igneous rocks, because we have a very, very unique geology around this area. When I was a graduate student, I did a lot of work in a laboratory. I was doing a lot of work studying sediments and how does water move through these sediments. And then I actually used that data to do some computer modeling to try to figure out where is this water coming from and where is it going? So what area needs to be protected in order to make sure that the water that's going into our bodies for drinking water is safe? And so geologists love going out into nature, and some examples of these field outcrops, this group of individuals is looking out at a large outcrop where the rock is literally cropping out of the ground. And so one of the nice things about going into geology out west is there's a lot more outcrops. We have a lot of soil around here, so we don't have as many outcrops. So geologists in Missouri tend to rely a little bit more on road cuts, which are where the road is cut away, and we're going to be identifying the rocks, that method. But if it's not limited to exclusively to geology, atmospheric scientists will go out and study storms, and oceanographers will go to the oceans. You got to go where the data is. Space is a little more difficult, and so a lot of times we'll use the remote devices to collect that data. And so when we take materials back into a lab, this allows us to look at them a little bit more closely. We can use microscopes to look at identify minerals that are microscopic. One of the things that you can do with one of these cameras is slice these minerals very, very thin, shine light through them, and identify them even if they're sub-millimeter in size. We can look at some different chemical analysis. We can do an atomic absorption, X-ray diffraction to look at the atomic shape of the crystals of the minerals. We can also use atomic absorption and to determine what elements we're dealing with. And so there's all kinds of different types of materials that we can do at a lab. And so they're not one is better than the other. They're both used in conjunction for different aspects. And then finally, we use computer modeling. Computer modeling allows us the advantage of running these scenarios again and again. But unfortunately, the computer model is only as good as the data that you put in. The physical model is also as good as the data that you put in. If you in this river model here, where they're using sand and water to simulate what river meanders and braided streams, if you don't put in good data, if you put too much water in it, if you don't properly model the landscape, you're going to end up with data that's not going to give you much information. So the scientific method is the first step in the scientific method is to recognize the problem. The second step is to collect data and use that data to formulate a hypothesis. And once you formulate a hypothesis, this hypothesis has to be something that can be tested. After you establish this hypothesis, you develop a test that you could actually do your test. And once you establish your hypothesis and test it and it becomes right, I'm sure you're familiar with this, it is elevated to a theory. And then if you have a theory, then it can be elevated again to a law. And a lot of scientists will just, or you may have said, well, this is a pretty step A, step B, step C, step D, but you're not really learning anything if your hypothesis is always correct. You really get a sense of knowledge and scientific breakthrough when our data doesn't match, when we end up with an anomaly, something that causes our hypothesis to get reanalyzed. It's great being patted on the back saying everything I've done is perfect, but in reality, that's not when scientific breakthroughs take place. Scientific breakthroughs take place when we end up with a hypothesis that's not correct, and we have to go back and rework our hypothesis, make an analysis in a different way. Some great examples of this is the discovery of radioactivity or penicillin, or the shift from a Earth-centered solar system to a sun-centered solar system. Now, in order to identify the Earth and break down and do these analysis, geologists, well, scientists in general like to group things together. And so we've got 5 different groups here that lend themselves really nicely to classification and order. And it helps, the more we try to put things in boxes, we can identify and classify them. And so we've got the geosphere, which is the solid Earth, all the rocks on Earth. The hydrosphere is all the water on Earth, both liquid and solid. The cryosphere is kind of a subset of the hydrosphere, just the ice, the frozen component of the hydrosphere. The atmosphere, all the air. And then the biosphere, all the life on Earth. Now, if I ask you, what sphere do you fit into? Most people would say it's the biosphere. But when we start looking at it, we breathe air. We're mostly water. We grow our food in soil, in the geosphere. We use all sorts of different resources in that geosphere. So it's great for using an Earth system to classify is good for some things, but realize it can get really, really messy really, really quickly. My favorite example of this is trying to organize and group things in nature. We all know what red is and what orange is, but if we start looking at the colors of a rainbow, where is the break point between red and orange? And we actually do have a wavelength that says everything longer wavelength than this is red, everything shorter is orange, but in nature we find out that science is messy. And so nature is very messy, I should say. Now, when we start looking at one of the proper ways to identify what's going on Earth, one of the things that we're going to be looking at is units of time. Now, we use things like minutes and seconds and years, but we have realized through radiometric dating and other techniques that there are some times that are much, much longer. When we start looking at geologic time, we're starting to look at things from the dawn of the Earth, believed to be about 4.54 billion years old. And we start looking at the universe is 13.8 billion years old. One of the other things that we're going to be dealing with this semester is in chapter 2, we're going to spend a lot of time talking about plate tectonics. And this is a very big overarching theme that has not been around for that long. In the last 100 years or so, we've really learned a tremendous amount about plate tectonics. More on plate tectonics later in chapter 2. But plate tectonics basically talks about the Earth is composed of a series of plates. Some of these plates contain continents and oceans on them, and they're moving around much like a hard-boiled egg that was dropped on the ground, and you have these different chunks or plates of these eggshells, and these shells can move towards one another, away from one another, and move apart. And if they're constantly moving, there's going to be a point that all the land masses might have been or would have been together, and we call these supercontinents. You may be familiar with the most recent supercontinent called Pangaea. So the last part of the semester is going to be dealing with astronomy, and it's going to cover planets and beyond our solar system. And so we'll talk about some of the similarities. How does the Earth fit into the rest of the terrestrial planets, which are the 4 inner rocky planets? And then if we start looking at the next four planets, those are the gas giants. And then beyond that, we have the exoplanets, these objects that are found beyond our solar system. Orbiting exoplanets are planets that are moving around a different star. Ours, we know that the Earth rotates around the sun, and there's lots of other stars out there. And so we can look at those other planets that are going around other stars. When we start looking at the sources of energy, whenever we identify what is the mechanism that is causing a system to move or react, there's a number of different sources of energy. We start looking at the topic of plate tectonics. The Earth, the deeper you go into the Earth, we're going to have more radioactive materials. And as we know, radioactivity gives off small alpha particles or beta particles, and they can cause vibration or radioactivity. We know that we can also compress materials, and gravity is a good force that can compress materials. And a great example of this in physics would be the ideal gas law. If you squeeze this air together, you're going to notice it's going to get warm. The temperature is going to increase. The molecules are going to be closer together, and they're going to bump into one another. Temperature is a measurement of energy. And so a classic example of this is to take a tire and inflate air pressure into a tire with a compressor, and you'll notice that the tip of the nozzle that is compressing this air will actually heat up. The converse of this is true if you've ever used a can of compressed air to clean out your keyboard or whatnot. If you squeeze a compressed air can, what you'll notice is that air expands, and the exact opposite, it's going to absorb that energy, and the can will get very cold. We have gravity, which is a force between any two masses divided by the distance squared. And so we will talk a little bit about tides in our oceanography chapter, and the cause of tides is the gravitational pull between the Earth and any other object in space. Most people will talk only about the moon, but the sun is also in space, and the sun's a lot bigger. One of the advantages, or the sun does, why most people talk about the moon is that it is so close. The sun is so much further away, and if you take a big number and you square it, again, the calculation for gravity is mass of the two objects divided by the distance squared. If you take a big number and you square it, you multiply it times itself, it becomes a really big number in the denominator, which means that the force of gravity is significantly smaller. So there is an attraction between any two masses. And then we also have external energy, and we're going to talk a lot about the sun providing us with things like photosynthesis and heating up the air unevenly, causing us to have winds. And so when we start looking at any topic in this class, we're also going to look at what is the energy source of them. And these are the three different energy sources. Now, when we start looking at these systems, if part of our modeling and understanding of science and forming a hypothesis is to learn how the Earth works, what happens if we start changing this system? And so these changes can be natural changes, say a flooding event or a hurricane, or they can be anthropogenic changes from anthro meaning human sourced or human origin changed. And so in this image here on the right, we have a landscape that was clear cut by by a bulldozer and removed the vegetation. As a result, we can see some gullying taking place and some soil erosion, and you'll notice quite a bit of that in that image here. So when we start looking at why does this matter to me, why do I even care about this class other than I need to get a college credit? And college credit's great, but earth science addresses a lot of other practical issues, one of which is it can have an effect on what is your risk factor. We're going to talk about the New Madrid seismic zone. We're going to talk about river flooding. We are going to mention hurricanes, but we don't really have to worry too much right now here in Missouri. But if you were to move further to one of the coasts, you may have to deal with more of this. In fact, we'll talk about which coast is more prone to hurricanes and why that is. We're going to talk about where you get your drinking water from. I realize that water comes out of a tap, and that's a great thing. But where did it come from, and how did it get there from the tap? How did it get to the water tower or through your well? And if it is, how do we know it's safe? What are some different things that we can do to help us make sure that our water is safe? That's my specialty. That's what I got my master's in geology in, and it was groundwater hydrogeology. And so we'll talk more about that later in chapter 12, I believe. We can talk simply as much as what is the weather going to be like? Why do we have these different seasons? Why is Missouri so highly variable in its weather? What is our risk for different natural hazards, things like flooding and earthquakes? And how do we interpret issues with social consequences? We can talk about some of the different minerals that we use. One mineral that has gotten a lot of press in the last couple of years is a mineral that is used to mine the element cobalt that we will use in computer applications, and mainly in cell phones and battery laptops, things that power on computers. And where are you getting this? Where is these elements come from? I've seen a number of different bumper stickers around the mineral area to say that really hit this topic really home. Is if it can't be grown, it must be mined. And there's some cobalt in some places that are mined from unethical child labor mining. And so there's lots of different news articles that we can kind of understand what are the social consequences for these different resources. And so there's lots and lots and lots of different ways that we can look at a news story and see how this relates to earth science. And finally, the earth is just one planet in the larger universe. And so how does this fit? How does the earth fit in relationship? So we are going to spend a whole chapter on earth and the mineral resources and energy resources. And a resource is simply something that we use, and they can be either renewable or non-renewable, as the name implies. Renewable means it will come back. Non-renewable means is once you mine it, it's gone. You're going to have to come up with a different source. And so is the use of these resources sustainable? Are we finding new resources at the same rate that we are consuming those resources? How do we extract and use of these affect the environmental quality? So we can talk about how coal miners excavate coal from a mine. We can talk about coal, how that coal ends up in an energy power plant, which is going to turn a turbine and turn water into steam and release some additional gases and the impact on those. If we start looking at this road cut, geologists use these rocks to tell a story. We're going to talk about this. I've heard of this a number of different times, that every rock tells a story. And by the end of the semester, I hope that you're going to be able to look at a rock and see what its story is, and how we can interpret those samples. And so we're going to learn to appreciate our surroundings, like road cuts. I think I've already mentioned those a couple of times, where the highway needs to be level, or as level as it can be, so they will blast out part of the road and expose, or blast out part of the hillside and expose this cut of road along the road, called the road cut. And so we can see an image of these different layers of rock and sedimentary rock layers. We can look at the beach and the interface between the land and the sea, and we can look at it, how these beaches change over time, what effect the oceans have on these beaches. We can look at clouds and use them for forecasting. And then finally, we can look at the night sky and see how our solar system, we can see things like constellations and planets, and see how we fit into the rest of that solar system. So at the end of each chapter, I have these class questions, and I'm not going to answer them, but your job is to go through and answer these questions. And when you're done with these questions, answering these questions, you can go into my Mac and use the take your lecture quiz. I will ask 5 of these questions, and you will have a limited time to take those 5 questions. The preview quiz, Prelude chapter, you can take as many times as you want. All additional quizzes, you'll be given 1 attempt. But here's the trick. If you answer all of these questions, you're going to know exactly what the quiz question is and what the right answer is. So I encourage you to go back and answer these questions. This one, you may have to use your textbook. We'll talk about plate tectonics. And one of the other nice things about geology is we use images, and this is not just geology, but all sciences. We use images and graphs in our textbooks, and those are really, really useful for giving you lots of information very quickly. So if you have any questions, be sure to contact me. If not, I will post chapter 1 here shortly.